class. This is on neural networks. Remember, in the last class, we looked at the basics of perceptron and recall that it was a linear unit followed by an activation function, right? So we had theta j xj, j equal to 0 to n. These are various inputs going from x0 to xn, and there is this activation function which we said initially we talked about the step function, but then we said this could be approximated by sigmoid, right? G of theta transpose x, right? And h theta x was nothing but G of theta transpose x, right? Where G is the sigmoid function, right? And then we said that this could represent interesting functions such as AND or NAND and so on, right? But to represent XOR, we needed multiple such perceptrons arranged in a layered manner. Okay, and the layered architecture that we drew was a set of perceptrons in one layer followed by another layer of perceptrons and so on and so forth, right? And then finally, there is an output layer, right? And these are all hidden layers, and this is the output layer, right? And each of these uh, units in the beginning of the network in the first hidden layer get all the inputs, and there are all kinds of cross connections between these units. I'm drawing some of them, but they are all connected. It's sort of fully connected network, right? And then the goal is to really compute the parameters of this network, right? There are thetas associated with each of these units in this network, and we want to compute the parameters. In particular, remember in the last class we defined j theta to be, where theta is the set of all the parameters in the network, to be yi minus o, and assuming there are multiple outputs, we said yil minus ol summation over l equal to 1 to r, and then summation over all possible examples, and then into divided by 2m, right? So this was our objective function, right? This is same, this is the squared error summed over all possible outputs. Okay, and then we said, how do we really compute delta j theta over delta theta, let me call it jk, where jk is theta jk denotes weight of an interconnection, right? So this is what we really wanted to do. Okay, let's move forward to the next slide. Now, to compute the gradient, we will divide this problem into two cases. And why is that? This is because if you think about it carefully, the the right, suppose this is your output layer, right? Let's say this is O1 to OR, and there are all sorts of uh, perceptrons here, right? And in some sense, j theta directly depends on these the j theta directly depends on the weights of the final layer, right? Because these interconnections directly sort of affect j theta, and therefore we can compute them directly. But the challenge really is, as we'll see, is the dependence of j theta on the weights in hidden layers is indirect, because it is through uh, multiple layers that the information is passed up to the final layer, right? And then the question is, how do we really compute j theta with respect to parameters in these hidden layers, right? Let me do this as okay. And for to simplify things, we also said that we will assume that m is equal to 1, right? Therefore our objective becomes yi minus I is gone now, right? Because there is one example, right? So y minus yl minus ol, this is ol square sum over l equal to 1 to r. So it's simply the squared error over r possible outputs, and we'll assume that in general we can take some or all the examples. If you are doing stochastic gradient descent anyway, in each iteration you take a subset of examples, and that subset could also be of size 1. Okay. uh, and again, this is just to simplify the notation, but the math works out as well for the case when we have more than one example. Okay, so some notation that we will use. So let us say that you have a unit j in the network, somewhere in the network, and this could also be sort of the output unit. We will have a general treatment, and this might be connected to some units in the previous layer. This will be referred to as upstream, right? And similarly, this unit will also be connected to some units in the following or in the following layer, and which will be referred to as downstream, right? We'll also refer to as neighbors of j, upstream neighbors of j and downstream neighbors of, right? I'll define that notation very soon. Also we'll define a quantity which is called net j, which is the net input into unit j. In some sense, we would like to separate out the impact of the linear combination theta j. uh, in fact, I have to define something more, theta j x j k. Let me just write it. I will define it very soon. K belonging to up neighbors of j, right? Here note that theta jk is weight of interconnection from unit k to j. Okay, and similarly xjk is input going from unit k to j, right? So theta jk is the weight of the interconnection from unit k to j. So k is an up neighbor of j, right? Let me also draw something here to ground things, right? So there is a unit k here, right, which feeds into, right, I mean, I can also draw an arrow into unit j, and theta jk is the weight of this interconnection, and xjk is the input that is flowing from this unit k to unit j, right? And we'll define net j as a sort of the net linear combination, coming into unit j, or you can also think of it as the net linear sort of combination that this unit computes. Okay, and also we will refer to the output of unit j as oj, where oj, it is not very difficult to see, will be g of net j. Why is that clear? Why is that? Because net j is nothing but net linear combination coming into unit j, which is theta j k x j k, and g is the sigmoid function, right? So the net output of unit j is simply the sigmoid function applied to the linear combination being computed by unit j. Okay. Okay, let's move forward. So what we are doing is we are defining bunch of notation. In fact, I can write here. So what we'll do now is we will try to compute delta j theta with respect to delta theta jk for all jk, right? Where jk are sort of consecutive units in the network, right? J followed by, right? This in turn will be computed in terms of delta j theta over delta net j, right? So in directly computing delta j theta delta theta jk, we'll express this in the form of the gradient with respect to net j, that is the net input into the unit j, right? This is the basic idea, and then we'll see why this really simplifies things. Okay. Okay, let's move forward. I might need that picture again, so let me draw that. Unit j and net j was defined to be some theta j k x j k k belonging to up neighbors of j, all these inputs coming in, and outputs going out from unit j, which is oj, and oj is g of net j. Now we are interested in delta j theta over delta theta j k. Okay. Now because we said we want to express this in form of net j, so I can apply chain rule by differentiating it first with respect to net j and then differentiating net j with respect to delta j k. Is that okay? Okay. This quantity uh, is delta summation over k belonging to up neighbors of j theta jk x jk over delta theta jk, which is equal to xjk. I hope that is clear, right? So therefore this derivative, which is delta j theta with respect to theta jk, can be written as delta j theta over delta net j. This is the quantity we compute, but to get the desired gradient, we will then multiply this by xjk, which is the input from unit k to j based on the current set of weights, right? So this can be computed based on the current set of weights, right? So our objective then reduces to compute delta j theta over delta net j for all units j in the network, right? And if we would have computed this, then we know we would have also computed the corresponding derivatives with respect to all the interconnection weights. Okay. Then, as we had sort of done it earlier, or given the intuition earlier, we'll divide this into two parts. The part A would be when J belongs to output layer, and then the second one, part B, would be the case when J belongs to a hidden layer, right? Those units which are hidden from the output, and this separation is exactly for the reason that I had described earlier, that units in the output layer sort of directly affect j theta, so the gradient could be computed directly, but for units in the hidden layer we have to do an indirect computation using an algorithm that is in fact the main subject of today's lecture, which is called backpropagation. Right, I should have mentioned this in the beginning of this class, that this is at the heart of pretty much any deep learning system today, this backpropagation algorithm. Like this whole idea of taking gradients from the output layer and passing it backwards up to previous layers all the way to the first layer. And this whole idea, the basic algorithm that we'll describe here, is at the heart of learning algorithms for all modern deep learning systems. So if we really understand this, then essentially we have really understood the crux of learning in many deep learning, pretty much any deep learning system. Of course, there are many more details which go along with the learning. Pure backpropagation may not work. There are more details about learning rate and many other um, parameters are required, but nevertheless this backpropagation computation is key to this kind of learning. Okay, let's proceed forward. Now, one more identity that we'll need is we will also need, at some point delta Oj derivative of that with respect to net j, right? And remember, Oj is nothing but sigmoid applied to net j, and we know the derivative of sigmoid is simply sigmoid into 1 minus the sigmoid of the input. Therefore, this is g of net j into 1 minus, let me write that clearly, 1 minus g of net j, which is nothing but oj into 1 minus oj written in a simplified form. Okay, very good. So let me proceed. Okay, so now let us compute, let us do the part A first, which is computing the gradient expression for interconnection in the output layer. So delta j theta over delta net j, right? Remember, we'll do it with respect to net j, and in turn we know how to compute the derivative with respect to each of the interconnections coming into unit j, right? And where j belongs to the output layer. Okay, so this is del or del net j of j theta. So we can write the expression for this, which is y l minus o l square, l equal to 1 to r, assuming there are r such outputs. Half of this, remember we are dealing with only one example. Okay, right? So this expression comes out to be, you can apply the chain rule. So this, note that only in this summation, only when j equal to l, that particular term will have a non-zero gradient. All other terms will vanish because other outputs do not depend on net j, that is the net linear combination being computed in unit j. Therefore, this will become half into 2 into yj minus oj right? Where essentially we have put j equal to L, that is the only term which will be non-zero, into delta OL over delta net. Sorry, this should be j, and of course there is a minus 1 here because yj minus oj derivative, square derivative is yj minus oj into minus 1 because oj appears negative in yj minus oj, right? So this is the expression 2 cancels, and therefore this becomes minus yj minus oj into delta oj over delta net j, as we saw earlier, is oj into 1 minus oj, right? Using the expression of the gradient of a sigmoid function, right? So this is our derivative of the error function with respect to net j, where j belongs to the output layer, right? We will now define, this is for all units, delta j to be minus delta j theta over delta net j, right? Therefore, for output layers, this becomes delta j is yj minus oj into oj into 1 minus j, right? So this is the derivative that we want in the output layer. So this is case A, very simple. Okay. uh, okay, now let us now compute delta j theta over delta net j, where j belongs to a hidden layer. Okay, and that we'll do in the next slide. Okay, so now let us consider a unit j in the hidden layer, and we will now try to understand its dependence on, or rather dependence of j theta on unit j, right? And remember the intuition, the whole idea of using this back propagation was the fact that this unit j, right, we have associated uh, quantity net j, and j theta does not directly depend on net j because there are other layers in between. In particular, we have units of the form, let's say unit L in the immediately following layers, that will essentially uh, determine its dependence, the dependence of j theta on unit j, right? And this will be the key idea that we'll use, that will express delta j theta over delta net j in terms of delta j theta delta net L, where L belongs to downstream neighbor of unit J. This is the key idea. And now you see the intuition that why is it called backpropagation algorithm, because presumably this quantity has already been computed, right? Because essentially if we go layer by layer, going from the output layer to the first layer, then we know that we have computed the gradient with respect to units in the immediately following layer or the downstream layer, and if we can express the gradient with respect to uh, the current unit in terms of the gradients in the immediately following or downstream layer, then we will be done, right? This is the key idea, right? And this is exactly the objective of this next part. Okay, uh, we also might need, we'll just keep it aside, unit k's which are sort of units in the immediately preceding or upstream layer, right? So unit j, immediately preceding layer is our units denoted by indices k, and immediately following layer are units denoted by indices else. Okay, now to do this, and note that there are multiple such else, right? That the information to j theta will pass through, the effect of net j will pass through multiple such net else which are in the next downstream layer. Okay, now to do this, we will need an aside. Maybe let me use a different pen. It may be darker one. Suppose I have a function f of y1 up to, let's say, y capital A, where each y small k depends is in turn a function of x1 up to, let's say, xn, right? So in particular we have a scenario where f is a function of y1 up to yk, where each y1 to yk is a function of x1 to xn. Okay, and let us say we want to compute, our objective is to compute delta f over delta xj for all xj, right? So we want to compute this gradient of the function f with respect to xj's, where the dependence on xj's is indirect and flows through y's, right? And you can see that the connection to what we really want to do in the case, right? And we will uh, let's go to the next slide. We will state this result without really proving it, right? This should be available in any book on calculus, delta x j, where each y small k is simit is a function. Let me use the one of x1 up to xn is given by, right? So this is simply an extension of the chain rule, where we differentiate f y1 up to y capital K with respect to, let's say, delta y small k into then delta y k over delta x j, sum over small k equal to 1 to capital K, right? So what is the idea? The idea is very simple, that you apply chain rule, that we know for a single variable. Recall, for a single variable the chain rule says that if your function f of y of x and we want to compute differentiation with respect to x, then this is simply delta f of y of, uh, let me write it slightly differently, uh, um, right? So delta f of y with respect to x, where y is a function of x, y is a function of x, can be written as delta f y delta y into delta y over delta, right? So this is the chain rule in the standard setting, right? So this is the standard chain rule, right? And the case above is sort of an extension, if you will, when dependence is through multiple variables. Is that okay? Yeah, right. And what is the idea? We are simply saying, you apply the chain rule for each y through which the information flows from x to the function f, and you apply the chain rule for each one of them and then simply add them up, right? This summation from k equal to capital K is that adding them, right? So this is a result that we will use for our computation. So now back to computing delta j theta over delta net j, right? And remember the picture again, right? This is unit j, and this essentially is followed by units of the form unit L's, which are units in the immediately following or downstream layers, and right, they essentially propagate the influence to j theta. Therefore, applying this generalized form of chain rule, we can write this as delta j theta over delta net L into delta net L over delta net J, and summation over all possible L's which are down neighbors of J, right? So this is back to computing, right? So this is our generalized chain rule, right? And this is what we'll use. We know this quantity that has been already computed. Uh, Already computed because of way we are structuring the computation, right? L's are all the units in the preceding layer, and this is the quantity that we will try to compute in the next slide. Okay. um, okay, next let us see how to compute this quantity, which is delta net L over delta net J. And for this, let us draw this picture again, where we have unit J, unit L, and this unit L is sort of the downstream unit in the layer following the layer which contains unit J, um, right? So, couple of observations here. First, note that the output of unit J is OJ, right? This is the net output that this unit produces, which is essentially sigmoid applied to the net input into unit J. Also, something very important to realize is that OJ is nothing but the input from unit J to L, that is XLJ. And why is that? This is because the input from J to L is exactly the output that this unit J will produce, which is OJ, right? So this will be a very important uh, fact that we'll use in the current computation, right? Therefore, delta net L can be written as uh, X Lj theta Lj summation over J belonging to up neighbors of unit L, delta of this with respect to delta net J. Okay, and because we just described that this XLJ is nothing but OJ, this entire quantity can be written as delta OJ into theta Lj summation over J belonging to up neighbors of unit L over delta net J. Now, what quantities in this sum depend on net J? Clearly, the only quantity which depends on net J is corresponding to unit J. All other units in the previous layer, previous to unit L, are unaffected. Therefore, all other terms vanish, and the only term that remains is delta Oj into theta Lj over delta net j. Now, theta Lj is sort of an independent parameter, which is the weight of this interconnection, and is not affected by net j. Right, net j in some sense only influences xlj, which is oj. Uh, Therefore, we can write this as theta Lj into delta Oj over delta net j, and which we know is theta Lj into Oj into 1 minus Oj. Right, so this is essentially the derivative of net input into unit L with respect to net input into unit, and this is something that we'll use in the next slide. Okay, so bringing the pieces together, we get this is for part B, hidden layers delta j theta with respect to delta net j can be given as delta j theta over delta net L into delta net L over delta net j summation over L belonging to down neighbors of unit j, and this quantity we know uh, is minus delta L, and this is the quantity that we just computed and is given by theta Lj into Oj into 1 minus Oj, right? Therefore, this entire expression becomes summation over L belonging to down neighbors of unit j into minus of delta L into theta Lj Oj into 1 minus Oj, right? And recall this is for units in the hidden layer, and similarly we also had for the units in the output layer, this gradient was given as delta j theta of with respect to delta net j was yj minus oj into minus 1 into oj into 1 minus oj, right? Combining these expressions together, we get uh, delta j theta with respect to delta net j, two cases A and B. A is in the output layer. This is given by yj minus oj into minus 1 into oj into 1 minus oj, and for the hidden layers this is given by summation minus delta L into theta Lj into oj into 1 minus oj, where L belongs to down neighbors of unit j. Okay, and here we have used the fact that delta L is minus delta j theta delta net L. Okay, this written slightly can be written as delta j, which is defined as delta j theta over delta net j. Therefore, for output layer, we have delta j is now we take the negative sign out. So this will become yj minus oj into oj into 1 minus oj, and for hidden layers, delta j is or can be expressed as uh, summation over L belong to down neighbors of j into theta delta L into theta Lj Oj into 1 minus Oj. Right, so this is what we will compute. This is in the output layer, and this is in the hidden layers. Right, and we also know how to compute delta J theta of with respect to the parameters theta delta theta jk, where jk is the weight of the interconnection from unit A to J, and this can be computed in terms of delta J theta delta net J as described earlier. Right, so this is sort of the entire computation, if you will, and this can be expressed in terms of the back propagation algorithm, which is described right here, which will proceed in some sense layer by layer. If we were to draw this architecture right here, right, these are my hidden layers, and let's say this is my output layer, and let me index them by t. Right, so this is t equal to 1 to t, and this final layer is the output layer, and the last hidden layer is capital T minus 1. Right, these are all hidden layers, and this is the output layer. Then to compute the gradient, which is essentially the backpropagation algorithm, we will first compute them. uh, right, so this is the first part, or part A, which is compute delta j for all j belonging to layer units in the output layer. Then this is part B. We go layer by layer backwards from t equal to t minus 1 to 1, and then compute delta j, where j belongs to layer t in terms of delta j primes, where j prime belongs to where j prime belongs to units in the layer t plus 1. Right, and that's it. That is the end of the for loop. Right, so this entire algorithm is essentially the backpropagation algorithm, which is computing first the gradients in the output layer and then in the hidden layers. And once again, why does this work? This works because we know the gradients in the output layer part A can be computed directly, because J theta directly depends on the parameters in the output layer. And once we know those, we can go one step back at a time, layer by layer, and compute the gradients in with respect to parameters in a particular hidden layer, in terms of the gradients in the exactly one following layer, or the downstream layer, which have already been computed, because we are going backwards layer by layer. And therefore we can compute delta j, which is minus of delta j theta delta net j for all the units in the network. And once we have this, we know how to compute delta j theta with respect to the interconnection weights uh, delta j theta delta theta jk, where theta jk is the weight of the interconnection from unit k to j. Right, so this describes the entire backpropagation algorithm that we will actually implement in our assignment. And I must say that this also forms, I guess I probably described this earlier, the basis of almost every modern day deep learning system. Right, so there are nuances, there are details, but if you have really understood this fundamental computation, then then essentially you are well placed to in fact implement pretty much backpropagation in any of the modern day deep learning architectures. As I said, there are more details in those architectures because they may not have sort of the fully connected layers, but they have a structure to these connections which will be described in the form of convolutions, or different kinds of structures such as RNNs, where the parameters might be tied across different layers, but that's the subject or topic that we'll study maybe a couple of classes later. Uh, in the remaining, let's say I'll take about maybe 10 minutes. I want to show you a few things. One is the kind of boundaries that these seemingly simple or at least the basic unit is very simple, these neural networks can learn. They can learn fairly complicated boundaries, and then I want to point you to or show you a couple of videos which essentially show the power of neural networks. One of them dates back to sometime in 90s, about self-driving cars. Of course, things have advanced quite a bit now, but it is still illustrative video from Carnegie Mellon. And other is also a very interesting video where it is demonstrated in the form of a child, or a network learning to speak, just like a child might learn to speak. So let's look at, and then this second one is, I think, part of the series which is referred to as machines that change the world. Right. So let us look at them in the next. Okay, so we will look at a few slides which have been borrowed from Pedro Domingo's course, machine learning course offered at the University of Washington, and I think these slides are quite illustrative in terms of what neural networks can do, and few of the remarks that I want to make about neural networks. So although I said I will show you a couple of videos about their cool applications, but maybe we'll do that in the next class. Let me go through some slides which I think are quite relevant. So this is a slide which is showing a multi-layer neural network, and here the goal is to learn the uh, learn to output text corresponding to words which range from head to hood, right? And the input is frequencies, right? Input can be thought of in terms of sound, so think of sound being represented using two frequencies, f1 and f2, and I believe this is a single hidden layer representation. So f1, f2, the inputs are represented by these two nodes, and there are a bunch of hidden layers in between. I mean, there is one hidden layer with bunch of hidden units in that layer, and as you can see, the sounds are very similar: head, hood to hood. And the goal is that given these basic frequencies, right, f1 and f2, which sort of represent your fundamental sound, can your neural network learn to identify the word which is being spoken? And on the bottom right or on the right side of this slide, you see the decision surface that is being learned. And as you can see, this is fairly complicated, right? So just with one hidden layer, you can learn something which is fairly intricate and complicated. And the picture, the dots are a little small, but you can see the different decision regions for the words going from head, HOD, had, and so on, heard, all the way to food. Right. So this is an illustration of that these neural networks can learn fairly complicated boundaries with just one hidden layer, and we'll talk more about that. So, okay, in this slide, I want to describe one example of neural networks. This is sort of a very simple example, but this illustrates, a very interesting idea about, what these hidden layers might represent. and this goes into modern day, what is referred to as autoencoders or networks, which can sort of learn hidden representations, latent representations, which can be much smaller than the original input. Right, so the task here is very simple. You have bunch of inputs, 8 inputs, and think of them as boolean valued. But what will happen is that we will represent, let's say, numbers from 0 to 7 using these inputs. Um, and the input is structured in a manner such that exactly one of the input nodes is 1 and all other are 0, right? So we really want to have just 8 input, and the output is also constrained to be same as input, right? So we just want to reproduce the output from the input. But the challenge here is that there is a hidden layer in between which connects these inputs to outputs, and this hidden layer has only three units, three perceptrons, right? So the question is, is it really powerful enough to represent this mapping from input to output, where we have 8 inputs to corresponding sort of 8 possible outputs, right? And if you think about it, that it is possible because we have only 8 inputs, and in some sense there is a way to encode them using 3 units if we think about binary encoding, right? So we can use 3 bits which are in the middle sort of hidden layer, and right, different combinations will different represent different inputs, and once you have represented them well in the hidden unit, we can sort of quote unquote decode them into outputs, which is again representing numbers from 1 to 8. So this is exactly describing what I just showed on the previous slide, from these 8 inputs, where each input is 8-bit number, but exactly one of them is one, others are 0. So there are 8 possible different inputs, and the output is constrained to be same as input, and we want to learn this. So here is what your hidden layer sort of learn after some amount of training. As you can see that because this the activation unit is sigmoid, so this is the output of sort of the hidden units. As you can, because these are sigmoid units, right? They will not go exactly to 0 or 1, but if sort of threshold around 0.5, then we can clearly see that hidden units are learning boolean or sorry, binary representation of these numbers. For example, the first one is 1 0 0, the second one is 0 0 1, then 0 1 0, and so on, right? So you can verify that these essentially are representing 8 different encodings of these 8 different inputs, right? Which essentially means that the network has learned to represent these numbers in binary, and therefore the next sort of the output layer essentially takes this binary representation and then decodes them, right? So we are able to encode the input into binary, and then we are able to decode it. And this is simply showing how learning proceeds. These are sum of squared errors for each of the output units, and as we can see that and on x-axis, I guess, we have the number of learning iterations, and as we can see over a number of learning iterations, the error goes to 0, which means the network has learned the desired function. And this slide shows the encoding, right, for one of the inputs, right? So if we give this input, how does the hidden encoding change over number of learning iterations? And as you can see, the initially network is sort of confused, right, or doesn't have the right encoding, and over the time it's slowly sort of learns the right encoding, where 2 of the hidden units go towards 1 and one of them goes to 0. Just verify this 0 1 0 0 0 0 number. I think this hidden encoding may be for a different input, so just correct that. But I guess the basic idea remains as shown here. Finally, before we break, I want to make a few remarks about convergence of backpropagation algorithm. In fact, this is an important point that I forgot to mention earlier. Is that or maybe I did mention that the error function for neural networks is highly non-convex because of this sigmoid function. Even just for perceptron and for neural networks, because it is composition of these sigmoids, it's highly non-convex, and gradient descent is only guaranteed to converge to local minima, and almost always probably not the global minima, and that may be a problem for learning these networks. Several ideas have been proposed. In fact, some of this material may be slightly outdated in the sense that this is for old school neural networks, and many new variations of these ideas, enhancements on these ideas have been proposed in deep learning models. Maybe we'll talk about them when we go to deep learning models, but there are ideas such as add momentum, where you sort of not just go along the gradient, but also you add a momentum term which will help you escape the local minima. Stochastic gradient descent can also help escape local minima because of the stochasticity. Other way to escape local minimas is to train multiple networks with different initial weights. Uh, Regarding these initial weights, which is also described in the next sort of bullet here, nature of convergence. Typically, this will also be important. Typically, we initialize these networks, the weights of these networks close to zero, and the idea is that hopefully when we are close to zero, the dependence on the input is very mild, right? So in some sense, we sort of go from a very simple function being learned to more complicated function, right? And this is typical in many learning algorithms. For example, in decision trees, you will start with a decision tree with single node and sort of expand it. And for neural networks, the simplest sort of parameters, in some sense, are zero weight parameters. So typically, you'll initialize parameters around zero, maybe not exactly zero, randomly initialize around zero, and that's what we'll do in our assignments, and then sort of move from there, right? So one way to train different neural networks to add the stochasticity would be sort of initialize, start with different initial parameters and see where what parameters are learned. And because of different starting points, and we are only guaranteed to converge to local minima, we may get to different local minimas, and maybe we could choose the best among those parameters um, by looking at a validation set, and then checking which sort of network gives us the best uh, accuracy over the validation set. And that's pretty much it, right? I already described that you start weights near zero and sort of make it more complicated as you go along the train. Finally, expressiveness of neural networks. You can show that they are quite expressive. In fact, every Boolean function can be represented by a network with a single hidden layer. That may not be very difficult to prove, right? In fact, think about this proof. You can also think of it as homework to formally prove that this statement is true. But in general, you might require exponential number of um, nodes in the number of inputs, right, number of hidden units, and that may not be desirable. Therefore, one way to reduce the number of nodes from exponential to much smaller is often to have multiple layers and not just one hidden layer. As far as continuous functions are concerned, every bounded continuous function can be approximated by a network with one hidden layer. Again, there is the number of units in that layer might explode, but theoretically, in principle, you can represent any bounded continuous function with arbitrarily small error using a network with one hidden layer. And any sort of arbitrary function can be approximated to arbitrary accuracy by network with two hidden layers. These are more theoretical results, but still useful to know about, to understand the power of these neural networks, which, as we have been discussing, also form the basis of modern day deep learning architecture. And for more details, the slides that I just covered, this material is based on the material described in Tom Mitchell's original book on machine learning, which came out in, I guess, somewhere in 90s, but some of the material is still useful. So feel free to refer to